Okay, today we're going to talk about metallic bonding. And so we're going to do two big things. We're going to talk about this electron C model of metallic bonding, and we're going to explain how bonding in metals and alloys affects their properties. Okay, and so metallic bonds, when we talk about it, the thing is we know metals bond with metals. Okay, and metals prefer to lose electrons. So it's just the question is how do two things that both want to give away their electrons bond? And so what we're going to see is that although they both prefer to lose electrons, they're going to kind of do a similar thing to covalent, where instead of one taking it, one giving away like ionic, you get where they're going to share the electrons, but in a different way. In covalent, they're sharing because each one is pulling those electrons away, and they're kind of tussling over, but sharing them both at the same time. In metals, everyone wants to give them away, and so they also share it, but they share it in a bit of a different model. And so what it is they share in this sea of electrons, we like to call it, which is all those metals give up their valence electrons. So if you had magnesium with those two valence electrons, all of them give them away. And so you have all these cation centers, right? Magnesium 2 plus, magnesium 2 plus, magnesium 2 plus. And floating around would be all the valence electrons, all right? And that stabilizes those cations. But it not only stabilizes the cation, it holds it together because an electron that's attracted to one of them is also attracted to the other. So you get this kind of ionic-like interaction with this covalent-like sharing, and because of it, they're kind of loosely tied together. And I say loosely because with those electrons moving around constantly, the cations are able to shift around if they want to. And so that's kind of what we can do with them, which brings us into the properties. Is those metals get held together by these free floating electrons, a sea of electrons that are moving around all the time. And so we have two main properties of metals, all right, which is malleability and ductility, or two that you may not have thought about or may not knew they had a name, but malleability and ductility. And malleability is that we can bang the metal into really thin sheets, or we can bend it and it maintains its strength. All right. Sheet metal is really, really thin, but really, really strong. And so the reason that we can do this, bang it into thin sheets, is that those electrons kind of act as almost a lubricant, allowing them to kind of shift over each other and move around, but stay strong, stay tied together with a series of bonds. Similar to the idea that if we tied all you guys in class together with like bungee cords, we can reposition you, move you around, and you're still stuck together, but there's this ability to move. All right. And ductility now means that we can pull it, stretch it into wires. And in the same way, if you guys were all attached and we grabbed onto one of you and pulled, well, the rest of you would kind of come along with, because there's that attraction of those electrons. But it doesn't have to come along with in this solid fashion. It can kind of pull one, and that one will pull on one, and that one will pull on one, and that one pulls on one. And because of that, we can pull it into a straight wire. Okay. The other obvious property with metal is that it conducts electricity, and that's really due to these free floating electrons, where when we have an electric current, it just pushes them one way or the other. So we get these electrons can transport, which is electricity. All right. And so these sea of electrons give metal pretty much all of its properties. All right. But even with this and this ability to move around, metals by nature have a very specific crystalline orderly pattern. They behave really similarly to ionic compounds in this way because you do have those positive cation cores, these negative electrons that float around, but these things like to organize themselves into very specific patterns. And I don't need you to know the patterns. I just put a few here to give you that example of, hey, here are the patterns that they tend to make And we can see, yeah, they are crystalline in nature. If you let metals cool, they come up with a crystalline pattern. If you see them in nature, sometimes they almost look like they're growing crystals, even as pure compounds. Okay? Now, one of the big things with metals that we can do is we can make these metal mixtures called alloys. And the reason we do is that most of our pure metals don't have the properties that we desire. So we like to wear gold jewelry, right? But gold is really, really soft. If you have pure gold, you can almost mold it with your hands. And so that wouldn't be good to wear around. You know, you have a ring on, you hit it off the table, and it's no longer a round ring, right? You have a necklace and it gets caught on your shirt and rips right off your neck. So having pure gold isn't great. So we mix in a few things, mix in a little copper, mix in a little tin, and it makes it stronger. That's why gold has a carat rating, right? 10 karat gold, 14 karat gold, 24 karat gold. That's the amount of gold in the mixture. And the less gold you have, the stronger it is. 10 karat gold is stronger because it has more of the other metals in it. Okay, but there's some things like steel and bronze and brass, right? We know with something like brass, we get that tone. All right, we're not making instruments out of copper, right? But you make that nice mixture and you get that nice tone. Okay, bronze, we know that we can mix together some copper and tin. We get a nice bronze. Okay, and then steel, which is any combination of iron and carbon, because iron, although very hard, oxidizes, it rusts. And so we don't want to have tools that constantly rust. So we mix in some different things and we make it prevent rust, like stainless steel, which has 5% nickel. And then you throw some chromium in there, and I believe it becomes surgical steel. And there's spring steel. The steel you build skyscrapers out of isn't the same steel that you build bridges out of, which isn't the same steel that you build your table out of. And so these are alloys, all right? And there's tons and tons of mixtures. So there are two main types of alloys, which is substitutional and interstitial. Substitutional is exactly what it sounds like. So what happens is that the atoms are a similar size, so we take one metal atom out and we put in another atom. Okay? It doesn't necessarily have to be a metal with alloys. Like when you mix for steel and it's carbon and iron, the carbon's a non-metal, so you can get some mixtures with that. But in this example, we have copper and zinc, right? Which we said was making that brass. And so we moved out the copper, put in zinc, okay? And we come up with this type of substitutional alloy, all right? The other one is what's called interstitial. And so the space between atoms when they're together, the space between is known as the interstices. And so in an interstitial alloy, a different size, a smaller molecule, or I mean a smaller atom, will go right into those spaces. Okay, so in this case, we're looking at steel. You have iron and these small little carbons, and the carbon actually fits in the gaps. And that's one of the reasons that the density increases with steel. So a cube, the same size for iron and steel, the steel will weigh more because we've shoved carbon in the spaces between those iron atoms. All right, we fit it in the interstices. And so as a whole, our alloys, when we have our pure metal, it looks kind of like this. Substitutional, we bounce one out, put one in. Interstitial, we put it in those in-between spaces, the interstices. And then a combination of the two, substitutional and interstitial, which is sometimes the case depending on what kind of mixture we're trying to make. All right, but the big thing is that these alloys are mixtures, and we, depending on what we want to do, we can make different combinations. There are millions and millions of alloys and combinations. Almost every metal that you use is some sort of mixture.